So as you were saying.
Sorry. Yeah.
Okay, got it. So I'm Eshkol from the Weizmann Institute of Science, just finished my PhD under the advising of Professor Ilan Koren. And today we'll talk about the long-wave cloud twilight zone, which is basically the cloud signature in the so-called, or what we suspect to be, clear sky. And I will soon talk more about what it is. So the outline for this talk will be, I will first talk about the cloud roles on Earth energy budget and climate, and then give an introduction to what is the cloud twilight zone, or how do we define it. And I'll present the cloud twilight zone in the long-wave infrared. Then I'll show my results of quantifying its radiative effect, and wrap up by talking about the implications for climate research and general remote sensing. So to start, this is a well-familiar feature of or figure that we all know, taken from the recent IPCC, where we can see the Earth's energy budget and the numbers. And what comes to mind firstly is that clouds dominate the radiative fluxes in the atmosphere. So they interact both with the solar radiation and reflect some of the energy back to space, but also interact with the long-wave radiation and cause a kind of a greenhouse effect. And of course, they also participate in the sensible and latent heat fluxes, which redistribute the energy in the atmospheric column. So in order to understand clouds' radiative effect in the simplest way, we can think of the two extreme cases, which are warm cumulus clouds and cirrus cold clouds. So the warm cumulus clouds, they interact very strongly with the solar radiation and reflect a lot of it out to space. And by that, they act to cool the planet, but they also interact with the long wave radiation or thermal radiation that is coming from below them. They absorb this radiation almost like a black body, and then re-emit part of it back to space, according to their temperature and according to Planck's function. But their temperature, as we can see here on the right, is quite similar to the temperature of the surface, and so their greenhouse effect or long-wave radiation effect is quite small. So in total, they have a strong albedo effect, but a weak greenhouse effect, and so they act to cool the planet. Cirrus clouds, on the other hand, are quite transparent for the solar radiation, but then their interaction with the thermal radiation causes a strong greenhouse effect because they have very cold temperatures. So they emit just a fraction of the radiation that is coming from the surface out to space, and by that act to warm the planet. And in order to quantify the cloud radiative effect of a domain, we can take the simplest equation given here, which is a function of the cloud fraction and also the difference between the average fluxes between clear sky and cloudy pixels, if we are thinking of a satellite image. And we know from what I've just shown you before from the IPCC reports, for example, that the cloud interacts strongly with radiation, both solar and thermal radiation. And so they have a strong local radiative effect. But if you look also here at few snapshots of a geostationary image of Earth, you can also see that Earth is a very cloudy planet, covered mostly by clouds. Actually, the exact number of what is the cloud fraction of, or the global cloud fraction, is quite mysterious, and this number is not that accurate or robust. Many studies have tried to estimate it over the years, and the only thing that they agree upon is that the cloud fraction is larger than 60% of the planet. So in every given moment, 60% of the planet is covered by these clouds, which we know that act strongly with the radiation. So all of this is just to say that clouds dominate Earth's radiation and energy budget. And we all know that they cause high uncertainty on climate prediction, coming both from the anthropogenic perturbation of the system. So again, this is taken from the latest IPCC report, where we can see the radiative forcing agents, and we can see the greenhouse gases effects which act to warm the planet. But also we can see the aerosol effects and their contribution or their effects on clouds. And we can see that clouds and aerosol act to cool the planet with the initial perturbation. And this is mostly coming by clouds, as you can see here by the purple bars. But another thing that you can notice is that the uncertainty is very high on the aerosol-cloud interaction, unlike the greenhouse gases. And if we look at the response of clouds to a warming of the planet, we can see that this is also very highly uncertain. As you can see here, again, taken from the latest IPCC report. So here we can see the most dominant feedbacks of the planet on or response of the planet to warming. So for example, we can see the Planck feedback and the water vapor and lapse rate feedback and the surface albedo feedback, and then we can see the cloud feedbacks. And I want you here to focus on the red arrow bars or the red bars, because these are taken from the latest IPCC report. And here you can see that while the uncertainty among most feedbacks is quite small, the cloud feedbacks uncertainty is very high. And I'll just note here that this uncertainty is not coming is not actually aimed to represent how much we are far from representing reality, but it's coming, this uncertainty is coming from the disagreement between our different GCM models. So it only means that our models do not agree on how to represent clouds and what will be their effect on radiation. So clouds are a significant source of uncertainty in climate prediction. And if we want to address this uncertainty and reduce it, we first need to understand what exactly is a cloud and maybe have better ways to approach it or to define it. So what is a cloud? So firstly, it can be considered as a subset of aerosols because by definition, aerosols are liquid or solid particles that are suspended in the atmosphere. So clouds as being just liquid droplets are part of it, of this definition. But in order to have a better separation between aerosols and clouds, we can also go to microphysical processes theory, such as the Kohler theory, which give us the critical radius in which a particle or a cloud droplet will grow unstably and continuously. So when a cloud droplet crosses a certain radius, it starts to grow, and you usually call it activation of the droplet and use it in order to separate between cloud droplets and aerosol particles or humidified aerosols and haze. But of course, this theory, this definition only is regarding every specific particle in a volume, while we know that inside clouds, we have many different particles and distributions of sizes. So in order to define a cloud in a specific domain, rather if it's in situ measurements or in modeling, we usually put a threshold on liquid water content, which is the amount of liquid water that we have in a volume. But this cannot be done when we are working with data of remote sensing because we don't have this information. So usually when we are working with remote sensing, we put a threshold on the optical thickness or the attenuation of radiation through the cloud in order to define in which point in space we have a cloud or we don't. And again, these two last definitions are highly dependent on the threshold number that we choose. And this dilemma that I've just shown you here is actually gets to the point of what is the cloud twilight zone that I mentioned before. It's these undefined regions in the skies, which cannot be directly or robustly defined as clear skies and aerosols, and also not as clouds. And the best way to give you some intuition to it and to visualize it is looking at this image of warm cumulus clouds that I've just taken with a simple camera from the surface. And here you can see that the sun was high in the sky. So the first things to come to our eyes is the difference between the clear blue skies and the puffy white cumulus clouds. But then taking a closer look, we can see that we have these kinds of clouds halo around the cloud. Also small cloud fragments in between the clouds, and even optically thin clouds that can be found farther away from the clouds. So in this case, these optically thin clouds, we can only observe it in a certain angle due to the forward scattering of these small particles, hazy particles, that are because the sun is right above the clouds. In different viewing angles, we will not be necessarily able to see it. You can see that the image contains a lot of these hazy features, which will not be easily defined as clouds. And the concept of the cloud twilight zone was brought up almost 2 decades ago in the first paper of Cohen et al. In 2007, where he determined this definition of the twilight zone. And he did a global analysis in which they took many pixels of global images of MODIS, and they treated only the pixels that were not defined as clouds by the MODIS algorithm. Then they sorted all the pixels according to their distance from the nearest cloud and plotted the average reflectance. In this case, it's the average reflectance in the near infrared. And what you can see here is that the closer you get into a cloud, you can see that the reflectance statistically is more likely to increase, which means and suggests that clouds somehow affect their surrounding radiative transfer. Mind here that this is the x-axis here is on a log scale, so this is an exponential decay, and they found that the e-fold of this decay is 10 kilometers away from clouds. So this is a pretty big distance away from clouds, in which clouds still interfere with the radiation transfer around them. Many other analyses and similar analyses were conducted over the years and all shown very similar results. So this plot here on the right, for example, gives the same analysis for different wavelengths in the solar radiation. And you can see the same response of the mean values of reflectance. As you get farther away from a cloud, you get saturated and you get kind of the background reflectance of the scene. And as you get closer to a cloud, you start to get more and more interferences of clouds. So this, of course, affects remote sensing retrievals and the estimations of clouds' radiative effect. More specifically, if you consider the equation that I've shown you before, in which treats clouds in clear sky in kind of a binary definition. So you have to determine what is cloudy and what is not. And then this is how you determine what are the mean fluxes or the cloud fraction. And if you are interested in this subject, so recently 2 very detailed reviews of this subject were published in BAMS in 2020. So you can refer to those papers as well. Over the years, the cloud twilight zone or albedo continuum or the cloud transition zone from clouds to aerosols, it has all kinds of names to this phenomena. And this was studied all over the years only in the shortwave radiation. And few mechanisms were suggested in order to explain how can we get this phenomena. So one of them is the 3D effect, which treats illuminations of clear sky by neighboring clouds. So since clouds are multiple scatterer, they can eject many photons from their sides. So for example, the photons will enter the clouds from their top according to the solar angle, but then the photons will experience many scattering events and can be scattered out to the clouds from its sides, where they can meet an air molecule or an aerosol particle and be scattered back to the sensor. And this will cause increased reflectance of pixels which are closer to clouds. So you can think of clouds as a kind of a secondary source of solar radiation to their surrounding. Another explanation is humidified aerosols, where we know that the relative humidity grows as we get closer to a cloud, and so the aerosol particles will grow by water uptake, which will enlarge their scattering cross-section, so they will scatter more radiation back to the sensor, and again will cause increased reflectance as you get closer to a cloud. And then another mechanism that was suggested is undetected clouds. We could be separated into sub-pixel clouds, where we can have a cloud that is smaller than the pixel of the sensor. And so the pixel of the sensor will have this kind of a mean value of cloudy and clear sky signals. And we can also have optically thin clouds, which can have a large extent on the horizontal dimension, but their attenuation of radiation will be quite weak. So they will be harder to detect. And as I said, this was studied, these phenomena were studied in the shortwave radiation or the solar radiation over the years, and we wanted to study and look how it looks in the long-wave infrared. So for this, we chose to work in the atmospheric window in the long-wave infrared, So firstly, talking about the long wave infrared, we are thinking usually most on wavelengths which are larger than 4 microns, as you can see here. And in the long wave infrared, the atmosphere is quite opaque to the radiation. And these panels here that you can see is the total absorption and scattering of clear sky atmosphere for radiation. And in the case of long wave infrared, it's only absorption. But you can see that we can have this minima here around 10 microns, which is called the atmospheric window. And this shows high transmittance through the atmosphere with only low absorption, which is coming mostly from water vapor and a little bit of ozone. Also, the atmospheric window, if we plot the Planck function curve for the temperature of 300 kelvins, which represent the surface of the Earth, so we can see that almost a third of the energy will be emitted from the surface inside the atmospheric window. So this is a very efficient way of Earth to cool itself, because a lot of radiation can escape out to space through inside the atmospheric window. And for this reason also, the atmospheric window is used to surface and water vapor retrievals, because you can actually see the surface or sense how much water vapor you have in the atmospheric column just by observing the atmospheric window in the long wave infrared. And all of this changes when you put a cloud in the atmosphere, because clouds absorb also in the atmospheric window almost like a black body. So they have to close the atmospheric window. And this is why we actually chose to work with the atmospheric window, because it will be sensitive to clouds and even to warm clouds. So in order to give a visualization of how does the cloud twilight zone in the long wave looks from space, we give you here this cumulus cloud image of MODIS, aqua, that is taken over the oceans, where you can see the white clouds and the dark ocean. And this is exactly the same image, only using the 10 micron channel of MODIS, which is inside the atmospheric window. So this is like looking with an infrared camera from space over the cloud field. So we can see that this ocean surface is warm, and this is where we can see the clear sky, and is approaching 300 kelvins. But the clouds themselves are in blue because due to their colder cloud top temperatures. So they emit less radiation out to the sensor or out to space. Taking a zoom in on a part of the domain, and then also using the MODIS algorithm in order to mask the clouds in white, we can actually get real good understanding of what is the cloud twilight zone. So for example, we can see this halo around the cloud that is found here. We can also see large scale and weak gradients from clouds into clear sky. And we can even see these reduced brightness temperature spots or isolated pockets of humidity or undetected clouds, which are found far away from clouds and not directly connected to a detected cloud. All of this together combines to be the cloud twilight zone in the long wave infrared. And in order to quantify it, we chose to work with the variable of distance from the nearest cloud. So for this, we take the RGB image and we come up with a cloud mask, or we use MODIS cloud mask in order to have a binary separation between clouds and clear sky, or the detected clouds in the clear sky. And then from this binary image, we can come up with the distance from nearest clouds map that is shown here on the right. And this is just to plot for this image and to give a sanity check for an analysis. We plot the green channel mean reflectance as a function from distance from nearest cloud. And indeed, we see that the closer we get to a cloud, we get higher reflectance values. And the new result here is to look at exactly the same thing, but in the long wave infrared, where we actually see kind of the mirror behavior of the curve. As far enough from the clouds, we can see the temperature or the brightness temperature of the ocean. But as we get closer to a cloud, we see a reduced brightness temperature, which suggests that clouds affect or reflect some kind of a greenhouse effect on their surrounding as you get closer to a cloud. And if we want to consider the long wave cloud twilight zone, we also need to consider what is the mechanism that force it, because they should be different, because the refractive index in the long wave sorry, will be different. and also the different ratio between the wavelength and the aerosol particle or the cloud droplets. So the 3D effect is mostly a scattering phenomena which can be neglected for small particles or small cloud droplets when we treat the long-wave infrared. So this effect can be neglected. We ran some tests in order to see what it can be the effect of humidified aerosols, and found that this also cannot explain most of the signal that we observed. So in order to give some intuition to it, you can think of it that absorption is proportional to volume. And because these particles are so small, their volume is also so small that it barely influences the absorption inside the medium. So we are left with undetected clouds, which are the main players in the long-wave cloud twilight zone. But this is not all of it, because as I mentioned before, we also have some water vapor extinction inside the atmospheric window. So high concentrations of water vapor can also contribute to the effect that we observe. And in order to estimate the long-wave cloud twilight zone radiative effect, we took images of satellite images of MODIS inside the atmospheric window. And for this, we came up with the method of treating the pixels as a kind of an independent pixel approximation. So each pixel in the image was treated as an independent atmospheric column. And if this estimation is correct, so the difference between the fluxes coming from the surface or emitted from the surface minus the fluxes going out from the top of the atmosphere will be the amount of energy and radiation that is absorbed by the atmospheric column. So the surface fluxes were estimated using the Planck function and using the MODIS SST product as the temperature that is plugged into the Planck function. For this, we took the 8-day mean SST temperature. And the top of the atmosphere fluxes were estimated using the satellite measurements, because MODIS sensors actually have 4 channels in the atmospheric window that measure in narrow band. So we came up with a methodology in order to interpolate these narrow bands, 4 channels, into a broad band inside the atmospheric window, and in order to estimate the fluxes from the top of the atmosphere. This was all being done keeping a conservative approach, which gives a lower bound to the total effect. So we know that we have a lot of assumptions here. So anytime we had to make some kind of assumptions in our calculations, we took the way that will lead us to an underestimation of the final value that we will obtain, or the final effect that we will calculate. So this only gives us the potential of the long-wave cloud twilight zone radiative effect. And now if we take the image that I've shown you before in the example, and we plot the radiative effect of all the pixels in the image as distance from the nearest cloud, and this is the radiative effect that we calculated using the methodology that I've just shown you. So we can see that we get a behavior of the curve that is very similar to the behavior that we've seen for the reflectance in many other studies. So far enough from the clouds, we can see that we have this kind of constant mean radiative effect of the clear sky. And then as we get closer to a cloud, we can see that the greenhouse effect is getting stronger and stronger. Another way to understand the cloud twilight zone in the long wave is to observe or to look at the histograms of different distance from nearest clouds beams, as you can see here. So here, for example, the blue histogram gives all the cloudy pixels. And here we can see that we get this B-model distributions of cloud radiative effect. So we have two different kinds of clouds with different radiative effects. Now we can also look at the histogram of all the pixels which are 2 kilometers away from clouds, which is given here in orange. And you can see the inherent feature of the cloud twilight zone, where you can see this overlap between the signals. So the signal of the weakest signals of clouds is equal to the strongest signals of what is supposedly, or in this case was defined as a clear sky. So in order to isolate the cloud radiative effect from the total radiative effect of the atmosphere that we've just plotted here, we just subtract the clear sky radiative effect from the radiative effect of each distance from nearest cloud beam. So first we have to define what is the extent of the twilight zone in order to define the clear sky radiative effect. And for this, we choose the distance in which the gradients of the curve and also the variability between different points in the curve is reduced to be insignificant. And this distance can be defined as the extent of the cloud twilight zone. Then we can take all pixels which are farther away from that distance and average them together in order to get the clear sky radiative effect, or kind of the background effect of the image. Then subtracting this background effect from each bin will simply give us the cloud's contribution to the radiative effect of each bin. And in order to consider the total, the mean radiative effect for the image, considering all distance from nearest cloud bins, we take this weighted average by considering the area fraction that each bin is capturing from the image. Because as you can see on the plot here from the right, we have much more pixels closer to clouds than pixels that are very far from clouds. And this area weighting factor just considers this. So obtaining this equation will just give us the total radiative or the mean radiative effect of the long wave cloud twilight zone in an image. Once we know the total radiative effect, we can also come up with a better scale of the twilight zone, which is the effective extent, where 90% of the effect occurs. In this case of the example image, it turns out to be around 7 kilometers. Now we can apply this algorithm for many images, doing a global analysis as we've done here for 6 days, taking 3 days from June 2014 and 3 days from December 2014. And restricting the data only to warm clouds, because as I mentioned before, this is part of the lower bound methodology. So we took only clouds over the ocean with a sensor viewing point that is close to nadir. And in order to make sure that we avoid cold clouds twilight zone, so we kept a safe distance from ice pixels from ice clouds and from cold clouds by taking 20 kilometers, by throwing away all the data that is within 20 kilometers from icy or cold clouds. These have left us with 353 warm cloud fields, which yielded a study area of around about 11% of the Earth's surface. And here you can see the distribution of the radiative effect of all the cloud fields that we analyzed, as seen here, with this box plot. So you can see here the red line is the median radiative effect for all images, and the black dot is the mean radiative effect for all of the images. The blue box here gives the 25 and 75 percentiles, and the arrow bar gives the 19 and 10% percentiles. So we can see that the radiative effect is confined to be positive, and the mean and median values gives a value of around 0.75 watts per meter square. And just to give you some intuition regarding to this number, it's proportional to an addition of 75 ppm of CO2 to an atmospheric column. So this is equivalent to a very strong clear sky radiative effect. And last, the interesting thing to do will be to see how much of the, what is the area fraction of the cloud twilight zone in the image. So the blue points that you see here gives you the area fraction of each distance from nearest cloud bin on average for all of the images. So for example, the 0 distance here gives you a mean cloud fraction of almost 30% for all images. And then this drops down quite dramatically and quite fast, because as I mentioned before, we don't have a lot of pixels which are far away from clouds. But more interestingly is to look at the cumulative distribution of the clear sky area coverage. So this is considering only the clear sky pixels in the scene or in the image and looking at the cumulative distribution. Now, taking the extent, the mean extent of the twilight zone for all images, which was about 11 kilometers, you can see that almost 90% of the clear sky are actually within the long wave twilight zone extent. And more importantly, taking the mean effective extent of the twilight zone, where 90% of the effect occurs, we can see that it still captures more than 60% of the clear sky, which basically means that most of the clear sky in warm cloud fields is influenced by the long-wave cloud twilight zone. So to sum up, the long-wave cloud twilight zone consists of undetected clouds and high concentrations of water vapor. Its fraction of the clear sky is about 60%, so it's quite loud. And we gave a lower bound estimation for the twilight zone radiative effect to be about 0.75 watts per meter square, which is equivalent to an addition of 75 ppm of CO2. And this is just another way to make the point that clouds dominate the radiation field, as the weakest radiative effect is equivalent to a very strong clear sky effect. As you can see also here in the distributions of radiative effect that were calculated. So it's important to know that these results are only for the long wave warming effect, and the total effect must be considered in order to know what is the net contribution of the twilight zone to the energy budget. But the significance of this lower bound estimation shows that the twilight zone needs to be considered in order to have a more accurate energy budget and climate prediction. It will also be important to study the sensitivity of the twilight zone to anthropogenic aerosols and to climate change in order to, again, predict climate change better, but also the energy budget in local scales, or such as weather scales. And a better understanding of the cloud twilight zone can improve remote sensing retrievals in the clear sky, because the twilight zone is expected to cause biases in those retrievals, as we assume in clear sky that we don't have any cloud interferences in the medium or in the path of the radiation. But if we actually do have some interferences of clouds, it can cause biases in the remote sensing products. That's it. Thank you all for listening, and I'll be happy to take any questions.